Thank you. Thank you, guys. Next slide, please. This is an outline. I'm going to highlight the topic that's going to be talked about immediately after this. Next slide, please. As you saw, this was to show you some new fabrications that have taken place recently. This is one fabrication, which is a silicon quantum computer by implanting individual single ions into a material. And you can see this here. These are implants of single phosphorus-31 ions. A number of people in the world are working on quantum computing. It's a very new technique, and it shows a lot of promise for the future of computing. Next slide, please. So this is what it looks like. These are the phosphorus-31 atoms, and this is just a scanning electron microscope image of the silicon quantum computing device. It's right here, and so this is the blow-up of that device. And you can see that it depicts a flip-flop qubit, they call it, which is coupled by electric dipole interaction. You can see the location of the phosphorus atoms, and you can see how the fields are changing because of the phosphorus in the material. Next slide, please. Another recent application is thin layers of semiconductors that can be folded. You may have seen these kinds of semiconductors. You take a piece of material, a silicon semiconductor material, and you implant hydrogen for 50, 100, 200 nanometers. And you get enough hydrogen in there, it just breaks apart because it's a gas inside this material. So the implant allows you to take off very thin layers, and these layers, some of them are even flexible. So that's a semiconductor on a flexible surface. Next slide. Microfabrications with high energy focused ion beams. So these are ion beams that are used to actually carve materials. So these are different kinds of materials. A and B are called negative resist, SU8, which can be shaped like this. And to see the scale, there's a little bar here. It's about right here. This is 50 microns. Down here, the bar is right here. That's 100 microns. And the second two materials, C and D, are made on a positive, they call it resist PMMA. So these can be done, and you can actually make, if you implant it correctly, you can have holes from this side to that side, and this side to that side. So you can see these small caves that go under the material. Next slide. Talk about some of the accelerator facilities we have at the University of North Texas and other places around the world that are used to do this ion implantation. Next slide. This is the main laboratory at our university. There's other laboratories that are associated with it, but this is the main lab. And there are two accelerators. You can see a tandem accelerator, which has 3 million volts in the terminal. You have some ion sources that are external for a tandem accelerator. Ions are produced, magnetically analyzed for momentum per charge here, passed through another magnet, momentum per charge analyzed there, and injected into the accelerator at a very low velocity, usually an energy of about 20 to 70 or 80 kiloelectron volts. Then accelerated to the terminal. If it's at 3 million volts and you have a negative ion here, you get 3 MeV of energy. You strip this carbon ion, say, of 3 electrons, so you get 3 times 3 going down the other side, so you get 3 MeV here and 9 MeV there. You get 12 MeV coming out this accelerator. It's in at a constant speed. It goes at a constant speed to another magnet, momentum per charge analyzed and changed direction into one of these beam lines, and you can see the names of the different analyses that can take place. Here is the high energy ion implantation that could be used for that paper, the talk I showed just a moment ago. We have another accelerator, which is a single-ended accelerator. The ion source is inside. It's a 3 million volt also, but it only accelerates gases. And they come out and they go down 2 different beam lines. There's 2 microprobe lines here for taking these ions and focusing into a small spot of 1 micron, a millionth of a meter, in order to do some of this work. Now, in addition, coming out of these 2 ion sources, there's a magnet here that gets the ions moving in this direction. If I don't inject into the accelerator, yet go straight, we go into what's called a low energy ion implantation line. And that's what we're going to talk about mostly today. Next slide. These are just the facilities. We're going to talk about the low energy ion implantation beam line. We can produce ions from 15 or 20 kilovolts up keV up to 80, say, keV. And we can produce all of these ions. Essentially any ion in the periodic table that we can make negative. If we can make a negative ion, then we can accelerate it out of the ion sources at a low energy and do the work. Now, for the tandem accelerator, of course, some ions don't form negative. You can't attach an electron to them. In that case, we can't make that ion. We can't make it or use it in the low energy ion implantation line. We can in the tandem accelerator because we can bring it out as a molecule, and we can make a negative molecule of almost anything, accelerate it into the middle of the accelerator, strip it of electrons, the molecule breaks apart, we take the part we want and use it for our experiments. But for the low energy implantation line, the ion has to be negative to get it out of the ion sources. Okay, next slide. So here's a depiction of the low energy implantation line. Here is this sputter source that makes ions of any element almost, solid or gas. Here's an albatross that's mainly used for helium. It's hard to make helium ions, negative. So they're both, either one can be used into this magnet, and they start down this beam line, pass through this magnet without deflection, and then go into this end station. Here's the end station. So it has things like slits to determine the size of the ion beam coming in. It has deflection plates to allow us to move the ion beam and up and down. And then it goes through a Faraday cup so we can tell how many ions we have, and on into the chamber where we have our target. And so this target will allow us to, because we have these scanning plates, to raster scan the beam across an area of about 3 or 4 square centimeters. So we just take the beam back and forth, just like a television screen. Television screen, you start up here, it goes across the other side, back down. The old television, do you remember? That's exactly what we do here, and it makes a very uniform ion implantation, and we do it many times, not just one pass. Next slide. Next slide, please. There's other laboratories associated with our lab, but next slide, I won't talk about them. There's other analysis laboratories that we use. We use these laboratories all the time at the Materials Research Facility and at the Research Park in the University of North Texas. Next slide. So you can't read all of these, but these are the research activities. These are the instrumentations that we have. This is the materials modification that we can do. This is the materials analysis. These are things like particle-induced X-ray emission, scattering transmission ion microscopy, Rutherford backscattering, and so on, nuclear reaction analysis. In addition, we can do all these modifications that we're going to talk about today. Next slide. So now we're going to talk about some of the principles of ion-solid interaction. What happens when an ion hits a material? A piece of silicon is very shiny, very smooth. When the ion hits it, it penetrates into the material beneath the surface. Next slide. So this is just a schematic of how this works. This is a substrate, say of silicon, and this is the fluence. This is the number of ions per square centimeter that are impacting on the surface of this material. And you can see the surface was right here. But as we get increased influence, you can see this arrow going across here. This is 10 to the 16 atoms or ions per square centimeter, 10 to the 17th, and so on, 10 to the 18th right there. As you can see, as you get more and more ions coming in and hitting the material per square centimeter, you start sputtering the material away. This causes a little bit of a problem, but it also helps us in another way. You can see that what's forming here in the substrate are some of these, what we call nanoparticles. The lower the fluence, the smaller the nanoparticle. The greater the fluence, the larger the nanoparticle. The greater the fluence, the more material is sputtered away. And so this just sort of shows you how nanoclusters and nanolayers are formed as the implantation fluence increases as we go from left to right. Then after you do all of this, then you come back in and do a laser annealing or a thermal annealing, a rapid thermal annealing. Next slide, please. So here's just an example of buried transition metals and nanosystems in silicon. So here's a silicon crystal, here's the substrate, here's the surface at the top. And so if we were to implant this material, like I showed on the previous slide, with smaller fluences and lower energies, it'd be right here. If we implant it with higher fluences and higher energies, then it would be implanted and it would be right here. Now this is a cartoon that shows you circles for these nanoparticles, but you know what happens is the ions that are implanted right here, it's more of a Gaussian function. You know, right in the center of the Gaussians where most of the ions are, and then it falls off. So we can implant different fluences of ions, different depths in the material. All I have to do is change the energy of the particle accelerator, and I can go from here to here. All I have to do is do it for a little longer time period, and I can make a larger nanoparticle. Now, why do I want to do this? It turns out that the larger the nanoparticle is, the larger the wavelength that it can intercept, the larger the wavelength that it re-emits. The smaller the nanoparticle, smaller the wavelength. Small wavelength means higher energy. So the higher energy photons that are coming into this material get absorbed right here. The lower energy photons of the longer wavelength get absorbed down here, and intermediate photons are in the middle. So what does that do for us? Next slide. We can actually do I'm going to show you a simulation of ion implantation profiles for some of these heavy ions, and then I'm going to talk about why I wanted to put those ions in at different places and form nanoparticles of different sizes. Next slide. First, before we do the experiment, we usually do a simulation. We do a theoretical calculation of a code that is very well known. This is a code that Biersack and Hagman wrote back in 1980. It's the transportation of ions in matter code. It allows you to calculate what's going to happen if you send an ion into a material, any ion, any energy. And it'll go up to about a GeV, I believe. And so it allows you to calculate, and I'll show you some more in just a minute. One note, the person that actually started using TRIM and then developed its companion program, SRIM, was Jim Ziegler. He's going to be honored in Cozumel, January 12 to 15 of next year, because he's sort of the person that started all of this. He's the one that took that TRIM program and made it so useful that any one of us can use it in about 5 minutes. You can put it on your computer, it's free, and use it to calculate what happens when an ion hits a material, any material. Next slide. In addition, we have some improved programs over that early program, 1980s. This is a dynamic trim, and this is a sputtering and dynamic trim. So what this does, you saw that slide about 3 ago, where we were sputtering into the material. We were eating the material away. Well, if you don't take that into account, you're not going to have the right answer. And I'm going to show you what looks like the wrong answer in a minute. So you have to take that sputtering into account. Next slide. This is just, I'm going to mention the challenge in low energy, high fluence ion implantation. These are the trim results. I know you can't read those. All these ions are at 50, this is all ion, hydrogen, helium, carbon, silicon, iron, silver, and gold. All ions are at 50 keV of energy. And what we notice, that I can tell you, I can read it, as the ion mass increases, the range of the ion decreases. As the ion gets bigger and it hits a material, it's not going to go as far into the material. That's one thing. The range of the ion in the material decreases. And what happens with the larger ions is you get more sputtering. So for hydrogen, there's no sputtering. It just goes into the material. You can't hardly sputter a silicon atom with a hydrogen atom. But you get on down here with silicon on silicon, or iron on silicon, or silver, gold, you can sputter a lot of the surface away, a lot of the silicon substrate. Now, at the same time, you're implanting the gold ions, say. As you implant the gold ions, another gold ion comes in. It can knock gold ions out and silicon ions out. So, that's what this little table shows you. Turns out we found out that you can get about 2 times 10 to the 17, I believe it is, I can't read it, atoms per square centimeter. And the range of those is like, for gold it's 20 nanometers. For silicon it's like 80 nanometers. For this 2 times 10 to the 17 at 50 keV. And here, this is the target atom sputtering yield per ion that comes in. Every ion that comes in knocks out 5.46 ions. One ion in at that energy and that mass knocks out 5.46. So you have to take this into account. That's why we're using this special program that allows us to take care of sputtering. Next slide. These are just some examples of the simulation using both of those codes. The black curve is the trim, the earlier code. This is for hydrogen, helium, carbon, silicon. Next slide. Iron, silver, and gold. Now notice the trim is still in here. Should be black there. And this is black. So that's what trim would say. That's what happens if you implant gold in silicon at 50 keV. They all pile up right here. Well, that's not what happens. What happens is you sputter the surface away, and the gold, these are different fluences. You can see the gold is right at the surface. The gold is on the surface as well as into the material, 20 nanometers. Next slide. So these simulations help us determine how we want to do this, how we want to make these materials. Now I'm going to talk about some examples of ion implantation in the synthesis of electronic, optical, and magnetic materials. And I'm specifically going to talk about silicon again, silicon carbide, silicon iron cobalt, as well as a little bit about nanowires. Next slide. So this is the synthesis and properties. First we're going to talk about solar photovoltaic materials, because we can make a better solar panel using this technique of ion implantation and have a higher efficiency. Next slide. This is a solar radiation spectrum. This is wavelength 250 to 2500 nanometers. And you can see this is the visible is this dashed line between here and here. That's visible. This is UV, this is infrared. And the sunlight at the top of the atmosphere is the yellow there, okay? But once it gets into the atmosphere, it starts getting absorbed by water molecules, carbon dioxide, carbon monoxide, other elements, nitrogen. And so what happens is you get the red. That's the spectrum at sea level. And this black line here is the black body spectrum that you would get if you had something at 5,250 degrees C. So what you'd like to do is make a material that looks at all of these wavelengths. You'd like not to have a solar panel that only collects a small band of wavelengths. You'd like it to collect a large band of wavelengths to make it more efficient. Next slide. These are just a list of graph of different solar cell efficiencies. You'll notice that the curves all seem to go up. They go up with a little positive slope. So they're improving. This is 1975 or so, up to 2015 or 16, 17. All of them are improving. They're all making improvements. But you notice that there's a big difference. The cell efficiency is, 12%, 24%, 36, 48, 52. So these are in the 40s for efficiency of energy that strikes the solar panel and gets absorbed. Most of the silicon work is down here in the 20s. And then some of those solar panels you can buy at Home Depot or someplace like this, they're not very efficient. They may be 10% efficient at best. But there's some solar panels, some that are very expensive, but they're very efficient. These are used on satellites, where you really don't care how much it costs. You want to have the energy to run the satellite. So you have these very expensive solar panels made up like this. Next slide. And some of those were multi-junction cells. I'm going to talk about that in just a minute or two. Okay, now we're back to this slide I showed earlier, showing the basic physical processes from left to right, how you make these larger and larger nanoparticles. So what we're going to do is we're going to look at the synthesis and try to understand the electrical, optical, and magnetic properties of these materials for device development. Next slide. So I've shown this once. This is the low band gap material, low energy, large wavelength. This is the high band gap material right in here, high energy, small wavelength. For these devices to be sensitive to the broad electromagnetic spectrum, it requires this range of nanoparticles at different depths in the material. And because the red long wavelengths travel further in the material than the high energy short wavelengths, you have to put the small particles near the surface and the larger particles deeper. And of course, as I mentioned, the size of the nanoparticle corresponds to the size of the wavelength that's absorbed. Okay, next slide. So, here is a tandem solar cell. It has 3 sections. So this is the first section is the top silicon. It's sensitive to 1.8 eV. The middle is 1.6. The lower is 1.4. This is something that was done and reported in Solar Energy Materials in 2000. What does this give you? If you were looking at the top, here's what you would absorb if you were to have just the top. If you were to have the middle, this is what you would absorb. And if you have the bottom, 1.4 eV, this is what would be absorbed. Now, If you have all three, you can integrate over all three and you'll get this curve. So we have what we're trying to find is this material that allows you to accept a large band of wavelengths from the sun. Next slide. Next slide. Okay, no, that's okay, thanks. So, why do we want to synthesize these metal clusters buried in silicon? It turns out that these nanoparticles scatter light over a broad spectral range that can be tuned by the surrounding dielectric material that it's in. So this just shows some scattering cross-sections of a 100 nanometer size silver particle that's embedded in three different dielectrics: silicon, silicon nitride, and air. And so you see it's a wide spectrum. So this is Harry Atwater and colleagues and published this in Nature. This is plasmonics for improved photovoltaic devices. Next slide. So, if we did a theoretical simulation of the distribution of the various energies of implanted silicon ions in silicon with different fluences to facilitate these various size metal clusters, let's say we've done this experiment. We've simulated by implanting 58, 68, and 78 keV silver ions into silicon. And they were, of course, had to be done at different fluences. And you can see, see if I can see the fluence here. I can't read it hardly. Looks like this is 10 to the 16, 15, 10 to the 2.5 times 10 to the 15. And this is 1.7 times 10 to the 15. I can't hardly read it even myself up here. So you can see what happens if you look at the trim. Here's trim. All these colored curves. And of course trim's not very good for silver because silver is a big ion, a large ion. And so you get this composite from the three curves there, the blue, red, and green. If you do the dynamic trim, you get, in this case, the blue line is on top of it, the red line, there's the green line, and then here's the composite. And so you can see that it's quite a bit different. It's close to the surface again. Next slide. So this is a high-resolution transmission electron microscope image of various layers showing the formation of silver nanoparticles of different sizes, different depths in the implanted region. And this sample was annealed at 500 degrees centigrade after multiple energy ion implantations. Now, what you can see here's the material, the amorphous material, and then after the implantation, it's then annealed at 500 degrees C. And what you can see in this picture is you see this curve here is what it looks like the amorphous material. It was implanted halfway through this 80 nanometer amorphous silicon on the surface. So, you know, most of them piled up right here in the middle. And then after the annealing, what happens is you can see a separation. Now it's this one peak is now two peaks. So the nanoparticles have moved toward the surface and moved further into the material. The smaller ones are on the surface. The larger ones appear to be further in toward the bottom of that 80 nanometer layer. And so this is just an X-ray line profile right here across this particle right there. That's one of the particles. I don't remember which one it is, but it may be that one. But it was a X-ray line profile, and it shows it to be silver. Next slide. And if you look at the distribution of these silver nanoparticles in the implanted sample after annealing for 90 minutes, you find, oh, this is the same picture. You can see it a little better maybe. There's the first peak, there's the second peak. The second B part here shows that it's a image from TE image from J image software package, and it looks like the larger diameter silver particles are in this region in the 40 to 65 or so nanometer depth, And the smaller particles are up at over here in the 5 to 20, 25. So it's done what we were trying to do. And of course, this is just the first shot at it. We need to do it again and do it more carefully. Next slide. So this is just an optical absorption spectrum from multiple energy silver implanted in the silicon and annealed at 500 degrees centigrade. So this is absorption versus wavelength. This is 200, this is 800 nanometers. And you can see that there's three peaks, A, B, and C, really. A, B, and then this big peak, C. Well, the A peak is right here. It's transitions in the material. B is the sharp peak is due to the silver nanoparticles, and C is another large peak of the nanoparticles. And so this is just a crystalline silicon. That's what you get. That's the absorption if it's just crystalline silicon. The black is the as implanted, and the red is after the annealing. Next slide. Okay, so enough about solar materials. We're going to talk about synthesizing silicon carbide and silicon nanocrystals and carbon and silicon dioxide, and then some single and dual ion implantation. Next slide. So here's synthesis of some of these silicon carbide layers by multiple energy carbon ion implantation. And you can see here a number of these different peaks, the concentration of the carbon for different fluences. It's a trim simulation. And then over here you can see X-ray diffraction of the implanted layer, this confirms the formation of the beta silicon carbide. Now what's silicon carbide good for? Well, most of our LED lights are silicon carbide. Silicon carbide is a very hard material. It's used for grinding tools. You go to Home Depot and buy one of the little grinding wheels to cut something. It's normally silicon carbide. Silicon carbide has some other properties. It's a high temperature material. It's a high voltage material. It doesn't break down at high voltages. And it's a high power material. It has high thermal conductivity and electrical semiconductivity. So it's a very useful material to be able to make. And it has electronic properties that are very nice as well. Next slide. Okay, here's silicon nanocrystals or nanoparticles. I'm not going to really talk about this, but it shows particle size and maximum photoluminescence. It sort of follows that curve. As the size increases, the luminescence decreases and the voltage decreases, energy decreases. Next slide. Okay, this is carbon implanted in the silicon dioxide. What happens when you thermally anneal it? This is a high-resolution TEM micrograph image taken at a depth of around 200 nanometers from the as-implanted sample, from the sample annealed at 1100 degrees for 10 minutes, and the sample annealed at 1100 degrees for 90 minutes. And you can see the nanostructures that are present there. Next slide. This just shows more of that. Here's some of the carbon nanostructures that have been made in this material. This is photoluminescence. Both of these is room temperature and low temperature photoluminescence for material that has at different annealing temperatures. It turns out the low temperature materials produce more photoluminescence, we found. Next slide. Okay, here's dual ion implantation. Here we're implanting 32 keV gold and 1.5 MeV gold implant and then annealing it. Gold and annealing it. Silicon implant and unannealed. So this is the unannealed, and the red is the gold and followed by 1.5 MeV gold and then annealed. So here you can see all three of the curves. So we get enhanced light emission from silicon nanoparticles when you have this dual ion implantation. Next slide. Okay, binary iron silicon and tertiary iron cobalt silicon systems. Next slide. So the reason we're interested in these materials is we think we can make them magnetic. We can by placing these materials in an external magnetic field and implanting it while in the magnetic field, we think we can make some rather interesting properties for this material. Next slide. So here is how that's done. Here are the north and south poles of a magnet. Here's the material. The field is this direction. And then the implant is coming in from perpendicular to the field. So the magnetic field is that you can just buy some very strong permanent magnets to do this. Next slide. That's just a picture of the field. Next slide. So the iron implanted in silicon. This is just a TEM image of the iron implanted sample, and you can see the X-ray diffraction spectrum showing the iron and silicon. Next slide. This is using X-ray photoelectron spectroscopy with an argon ion to produce clean it. So this is a spectrum that's collected at an optimum concentration range of like 40 nanometers from the surface of iron and cobalt implanted silicon that's annealed at 500 degrees centigrade. And you can see all the peaks telling you that it's iron and cobalt and silicon. The background is this right here, and that had to be subtracted. Next slide. That was photoluminescence. Now this is one of the first indications that we have had that we've been able to make something that has a magnetic dipole. And so here is the picture that goes from binding energy of 86 to 98. So that's this spectrum just blown up a little bit, and you can see right in here, there's a little bump. And so this is indirect evidence that there's a local magnetic moment in the material that we've produced. Next slide. So this is, again, X-ray photoelectron spectroscopy of ion beam sensitized iron, cobalt, and silicon. And it shows, here's the iron 2p peak and the cobalt 2p peak. So these from the X-ray photoelectron spectroscopy. Next slide. The magnetic properties. This is it's like a hysteresis curve, and we can see that there's some magnetic properties associated with these materials. Next slide. I guess the last thing I'm going to talk about is silicon nanowires. So what we've done is here are the nanowires on this surface right here, and then we've implanted cobalt and iron into the silicon nanowires. And the sputtering effect affects these nanowires, and what happened, the implant det that we implanted simulated the schematic formation of this tertiary metal silicon material. And we started with 150 nanometer silicon wire, and then after the implantation it's down to about 75 nanometers. So what's happened is the outside structure of that wire is just simply falling off of the wire. So we've been able to affect the size of these nanowires just simply by doing this ion implantation. Next slide. So here's as implanted, here's after annealing, and after annealing is when the wire gets half the size, half the diameter. Next slide. Okay, I'm going to finish on time, it looks like. So this is just hopefully to provide you with a glimpse of what you can do with ion implantation at anywhere that has a particle accelerator or a way to make these ions move. And they don't have to be very high energies. As you see, this is all done with 20 to 80 kilovolt keV ions. And we've done simulations to try to figure out what we need to do and what materials to use. And we found that we can, under external magnetic fields, we can enhance the formation of magnetic clusters in these iron-3 silicon alloys. And of course, we're still going to work on nanowires some more. We just began that. Both narrowband and broadband emissions are possible directly from silicon with the synthesis of these silicon nanoclusters. Low energy, high fluence ion beam implantation offers an attractive synthesized process for fabrication of near surface buried metal nanosystems in not only silicon but in almost any semiconductor material. For iron silicon and iron cobalt silicon, the valence band spectra reveal distinct features such as the higher density of states at the Fermi level, the existence of local magnetic moments for these metallic and ferromagnetic phases. Next slide. Thank you.